In today's note, we're going to be looking at comparing distributions. So our goal today is to be able to look at different scenarios and identify what type of distribution we should be using. Before we get into that, let's look at hypergeometric again, just as a little bit of a review from our last note. So a pencil case contains 14 yellow, 6 green, 10 purple, and 12 red markers. What is the probability that we select 3 purple markers when we grab 5? We could try to reason through this using our probability and understanding of combinations, or let's look through at our hypergeometric variables. So A, X, N, and R. A is going to be the total number of possible successful outcomes. Because we're looking for purple markers, A will be 10 because there's 10 purple markers in total. X is going to be 3 because that is the actual number of successes we're looking for. N refers to 42, or the total number of outcomes, and R is going to be 5 for the number of dependent trials we have. So the probability of 3 purple markers is equal to A choose X times N minus A choose R minus X all over N choose R. And if we work this out, we get 10 choose 3 for our purple markers times 32 choose 2 for our unsuccessful options, or everything but purple markers, all divided by 42 choose 5 for our total number of outcomes. So if we go through and calculate this, we get 0.0699, or 6.9% or 7%. B, what is the probability that we select 2 green and 3 red markers when we grab 5? So this one's going to be a little different because we're referring to 2 different things, or 2 different successes. So I can't really use the variables from before because I have multiple successes. However, I can use the same idea. So the probability of 2 green and 3 red is going to equal, and I'm going to look now at my number of successes. So for green, I have 6 total green, and I'm choosing 2 of them. Because it's and we should know it refers to multiplying, so I'm going to multiply by my red options, which would be 12 successful options for red, but I'm going to only choose 3 of them. And we're going to include in the end 24 choose 0 for all the other options. There's 24 unsuccessful options, but I'm not choosing any of them for my 5 markers because I want to look for the probability of choosing these 5, the 2 green and the 3 red. I'm still going to divide by 42 choose 5. If I work through this, I should get 3,300, all divided by 850,668, which works out to 0.003879, or 0.39%. So a very small percent chance of getting 2 green and 3 markers when we grab 5. In the other example, or next question, what is the expected number of red markers pulled from the box, or pulled among 5? So in this case, the expected value is equal to R times A divided by N, which works out to 12 red markers five dependent trials times 12 red markers. Again, order doesn't matter, but I just want to make sure it lines up with our variables, divided by 42 total options, which works out to 1.42. So therefore, expect 1 to 2 markers. Right. So again, the idea of this note is to be able to distinguish between the different types of variables. So in order to do that, we want to see what is the difference between them. So again, we have our three different types: binomial, hypergeometric, uniform. What they all share in common is the fact that they all deal with discrete or counted items. We will look at continuous probability distributions in a later unit though. Some key things: binomial distribution refers to independent trials, and we're looking at probability of success that does not change, and it has a different expected value. Hypergeometric, the key difference here is that there are dependent trials and that the probability of success changes. Again, a different expected value. What hypergeometric and binomial distributions share in common is that X is referring to the number of successes and that there is a fixed number of trials. For uniform distribution, again, uniform distribution refers to we have a number of items and the probability is always going to be 1 over n because they have an equally likely chance of it occurring. And again, the EX or the expected value is going to be different as well. So if you are unsure again of what these are, I'd go back into our previous notes and take a look at the specific characteristics of each type. In this flowchart, we can use this to help us figure out which type it is by answering some of these questions. So first we want to start off with, is it discrete or not? If it's not, then there are no probability distributions that we know of so far, or in this unit anyways, that we can use. If it is discrete, then we have to look for success or failure trials. If there are no success or failure trials, then we look for if each outcome is equally likely. If they are equally likely, then yes, and it is uniform. So we have our expected value formula of the sum of each outcome times the probability of that outcome, and our probability formula is equal to 1 over n. If the outcomes are not equally likely and it's not a success or failure trial, there is no specific type of distribution. It may be something like the lottery questions that we looked at in the past, so you don't need specific values except for the expected value formula. If it does contain success or failure trials, we need to look at if the trials are independent or not. If they are independent, which means they don't rely on each other, then it's a binomial distribution, and we're dealing with the formulas EX is equal to n times P, or the number of trials times the probability of success, and our probability distribution formula would be n choose X times P to the power of X times Q to the power of n minus X. Finally, if it's hypergeometric distribution, that means that there are no independent trials. The trials depend on each other. So that means we're dealing with the formulas for expected value of RA over N. And for the probability, it was A choose X times N minus A over R minus X, all over N choose R. So again, just a flowchart to help us try to figure out which formulas to use. Now we want to get into some classification and trying to identify which type of probability distribution we should be using. So for A spinner has 10 equally likely spaces numbered 1 to 10. The random variable is the number the spinner lands on. So in this case, the key thing that should jump out is the 10 equally likely spaces. If something's equally likely, that means our trials are uniform or have the same probability. So it should be uniform distribution. If we were to create a table or probability distribution table, again, we would have our outcomes 1, 2, all the way down to 10, and our probability for each outcome would be 1 over 10 because it's equally likely. In this case, we'd be using for our expected value formula the sum of each outcome times the probability of each outcome, and that would be all we could do for this scenario. In B, a class of 20 students, or in a class of 20 students, 12 play hockey. 6 people are chosen at random. The random variable is the number of the number of hockey players in the selection of 6 people. So if we look at this, there's a success or failure trials. So success is that you're on the team. Failure would be you're not on the team. So out of the people that I select, are they on the team? This is a dependent trial because as I remove one person from the class of 20, or as I pick one person from the class of 20, the probability changes. The probability should increase if I don't pick a hockey player, and it should decrease if I do pick a hockey player based on whoever is left. So in this case, it should be hypergeometric, which in this case, I need to find an A value, an X value, an R value, and an N value. So my A value, what is it? My total number of possible successes. There are 12 for the 12 people that play hockey. X, what is the actual number of successes I'm looking for? That could be either 0, 1, 2, 3, 4, 5, or 6, depending on what we're looking at. Our R, or number of trials, is 6, and our N, or total number of possible outcomes, would be 20 for the 20 students in the class. In C has 12% of the population are left-handed. The random variable is the number of left-handed people in 50 people. So here, there's a success or failure trials, right? The success is either they are left-handed or they are not. These trials are also independent because one person being left-handed does not influence the other person being left-handed. Or if a person is right-handed, it does not influence another person. So because they're independent and they're success or failure trials, this means it is a binomial distribution. And in this case, we would need our P, our Q, and our N. Our P value is the probability of success, which in this case is being left-handed, which would be 12%. Our Q would be then 1 minus 12%, or 100 minus 12%, which works out to 0.88. And the number of trials in here would be 50 for the 50 people. In D, a bowl contains 10 red marbles and 10 blue marbles. The random variable is the number of red marbles in a selection of 5 marbles. So here it is success or failure again. The success being a red marble, the failure being not a red marble. These trials are dependent because as one marble gets picked, the probability changes for the next one. Because it's a success or failure trial and they're dependent, that means we're dealing with hypergeometric distribution. So that means I need to look for my A value, my X value, my R value, and my N value. My A value in this case would be the 10 for the 10 total red marbles. My X values would be 0, 1, 2, 3, 4, or 5, because I have 5 marbles that I'm picking, so I could have either 0, 1, 2, 3, 4, or 5 red marbles chosen. My R is 5 for the 5 times I'm making a selection, and my N would be 20 because there are 20 total options. Finally, in E, a game consists of rolling a 12-faced die and receiving the dollar amount equivalent to that roll. The random variable is the number that the die lands on. So here, a 12-faced die, and we're looking for the number that the die lands on. There is no success or failure in this case because it is not a failure if it lands on a different side or a side other than something specific. So any side or face it lands on works. And because there is no success or failure, and everything is equally likely, we should be looking at a uniform distribution. So in this case, if I wanted to come up with a table of values or a probability distribution table, my outcomes or my x's would range from 1 all the way to 12, and our probability for each outcome would be 1 out of 12 because each outcome would have an equally likely chance of occurring. And if I wanted to find my expected value, it would be the sum of each outcome times the probability of each outcome occurring. So again, we weren't really trying to solve any of the questions, just understand what type of distribution we should be using. So if there was a question associated with it, we would be able to use the correct distribution and solve. So again, it does require you to read the questions and underline key information to really figure out what we're dealing with.